and YouTube sometimes. We've been talking about volumes of a revolution. I want to talk some more about that today. Remember, the basic idea of this is you have some function, some piece of a function from A to B, and when you rotate that, revolve it around the x-axis, it makes a big kind of a volume like this. And the volume of that thing, there's a formula for that. It's pi integral A to B f of x squared dx. The formula basically comes from just doing pi r squared. And you, when you do the integral here, you imagine you are slicing this thing up into vertical slices, which individually look like kind of solid discs with some thickness to them. They're actually cylinders. But anyway, the volume of one of those discs is basically it's pi r squared times the thickness, which is why the integral ends up looking like pi r squared. We did a couple examples last time. I want to do a couple more, and we're going to make this a little bit fancier. So this is actually the simplest form of this picture, but I will just say this is when revolved around the x-axis. And we are going to do some fancier versions of this where we revolve around some other axis. When we revolved around the x-axis, and this f of x, remember, refers to the height of the original function. That's what f of x means, of course. All right. Okay, anyway, I had just one more example. Last time we did one example where we found the volume of a sphere, a particular sphere of radius 2. I don't know if anyone noticed. I messed up the numbers in that one. I don't know if you wrote this down. I wrote the number 32. It should have been 24. I did 8 times 3 is 32, but it's not. It's 24. But anyway, let's try the volume of a cone. This is just one more example using that formula up there. The volume of a cone, all right? I'm going to, a cone is like this kind of a thing, right? There is a formula for the volume of a cone. I don't know if anybody knows this formula. So the cone has a certain radius and a certain height, right? Anyone happen to know the formula for the volume of a cone? I don't actually care if you do or not. This is not a formula that I typically have memorized, but the formula is the volume is 1/3 pi r squared h. That's the formula. I don't want to use that formula though. I want to actually derive this formula. So let's derive this by using the volume of revolution formula. All right. If we are to do this, it means you have to somehow imagine the cone as the result of this kind of revolving around the x-axis. So can anybody suggest what is the curve, what is the function that you have to start with so that when you spin it around the x-axis, the volume that you get ends up being a cone? Any ideas? Yeah?
Maybe a straight line.
Yeah, a straight line, she says. We will revolve a line, a straight line. So it would look something like, sorry. A line. Like that, right? Because if you take that line and spin it around the x-axis, it does indeed make a cone. So it's like this. I drew the line on the bottom, but actually all we care about is the line on the top, right? Because then you spin it around, you get the whole cone like that. Can we be specific about this line? We're going to, now for the sake of deriving this formula, I'm actually not going to use any specific numbers. I'm not going to talk about a cone with radius 2 and height 3 or whatever. I'm not going to use any specific numbers. I'm going to leave R and H as sort of unknown constants the whole time. All right. So the r and the h will appear inside of the integral, but they're not the variable, they're just constants, and we'll eventually treat them like constants, and then they'll just like appear as part of the answer, the r and the h. All right, I'm going to leave the r and the h as constants the whole time. Now, this line, we need a specific formula for the line. That line better have a formula, because we're going to have to plug it into an integral and then do the integral. A formula for the line. I don't know about you, I like the old mx plus b formula. That's how I roll. This is the slope and intercept form. What should I use for the b here?
0.
0, yeah. This is a line through the origin. In fact, if your line didn't go through the origin, you wouldn't get a cone. You would get some other weird shape. So, yeah, I'm going to use b equals 0 for my line. And what about the m? Here we got to be a little specific, or a little. We got to do something to figure out what the m is. I think we can label certain things on this graph. Like if the function goes out to there, of course that's 0 on the left. What's the x value over here? Remember, like I'm not asking for a specific number. Everything we're doing here, remember I said, is going to be in terms of r and h as constants. What is this x value here? It would be h, yeah. That's the height of the cone, right? Really, I'm taking this picture and kind of turning it sideways. So that's h. And where is the r on this picture? I think the r represents this height. I mean, it looks like a height when I draw it this way, but that's the r, right? Because that's the r on the original cone. It's the radius of the circle at the bottom of it, which when I turn it around, it looks like this. So that's the r. At this point, I think you can actually say what the m is. M is the slope of that line, which is like the rise over run. What would the m be here? It is the rise over the run. Yeah, I think that's r over h, right? R is the rise and h is the run here. So this is r over h. All right, so my function is f of x. This is what will eventually go inside the integral sign, right? It is f of x equals r over h x. All right, that's the function that we're going to work with inside our volume formula. Okay, great. And I think actually we can let's just do it then. So it's the volume is integral. Remember, I'll put pi on the outside, and then r over h x squared with a dx. And we should discuss what are the integration boundaries. That is, and this again you can see on the picture. Any ideas? What do you say?
0 and h.
0 and h, right. The leftmost x value is 0, and I'm going all the way across to the end. The other end, which is x equals h. So 0 and h, like that. All right? A lot of letters in here. X is the variable. Everything else we're going to treat like it's a constant, and we're just going to, those constants, the r and the h, are just going to appear as part of the answer. So let's try to do the integral. I got pi here. Integral 0 to h. On the inside, let's do the squaring. You don't have to do the FOIL or anything like that because it's not added in there. It's all just multiplied, which means every number you see there gets squared. So it's r squared over h squared times x squared dx. All right. How are we going to do this integral? Any ideas? If it was just x squared there, I would feel okay. What about those guys? Yeah?
Those would just be like constants, and you would just add 1 to 2 and then multiply by that.
They are just constants, she said. And then she said something that I didn't fully understand. But yeah, these are just constants multiplied on the inside of the integral. So what do you do with a constant multiple in an integral? You can take it outside of the integral. So that's what I'm going to do here. Pi r squared over h squared is just a coefficient now. And then all I got is integral of x squared. And how we do that is, as always, you increase by 1. I think this is the other stuff that she said. You increase to x cubed, and then you divide by 3 in the front. So I get, and these guys just stay like they are forever. We'll simplify at the end, but nothing's going to happen to them. 1/3 x cubed, and then I plug in 0 and h. This is a little weird having, these kind of constants inside the integration boundaries, but it doesn't really matter. You just do what we do. You plug in h for x, and then you subtract, and then you plug in 0 for x. So, and we're getting close to our final answer here. I got pi r squared over h squared times 1/3 h cubed. That's when I plugged in h for x. And now I go minus, same business, but instead of h for x, I put 0 for x. Pi r squared over h squared times 1/3 times 0 cubed. All right. This is basically the answer. Can we maybe just simplify a little so that we'll see that we got the correct formula? All of this business is times 0, so that is all just going to be 0. The first part, you can simplify a little bit because I have h squared in the denominator and h cubed upstairs, so we can cancel the h's, and it's just going to be pi r squared times 1/3 times h. And wouldn't you believe it? That is the formula for the volume of a cone, right? Pi, I said it before up here, 1/3 pi r squared h. That's what, if you just rearrange the ordering, that's what it is. All right. Any thoughts about that? Excellent. I find it, I don't know about you, I find it kind of satisfying that we can derive these old school formulas. There's a satisfaction in figuring it out. I hope everybody can relate to that. All right, great. I had a mathematically satisfying this moment over the weekend, actually. I like to make sliders. And I don't know why, like this is always, I never realized this until this weekend. I've been making, sliders on the grill for many years. But the sliders, these are like small burgers, right? If you're familiar with sliders. Just based on how big I make them and how big the cheese is, I always have one piece of cheese that's enough for 2 sliders. So I have a square piece of cheese, and I have to somehow divide this square equally across the 2 sliders, which is a little unsatisfying. I would like to put a square of cheese on each of the 2 sliders. But starting with a big square, you can't make that into 2 squares of half size, right? You know what I'm talking about? Anybody have a great solution to this? For some reason, it never occurred to me.
I mean, you can cut it in half into like 2 triangles if you wanted.
Cut it into 2 triangles. Yeah, this is what I should have realized long ago. You cut it that way. What's so great about that? My burgers are not triangular shaped.
You can fold in the outsides if you want.
Fold in the outsides? I don't like this idea. There's a better way. You got another suggestion?
Divide into a rectangle and then make each rectangle into 2 squares. Then you just put them on top of each other.
So what she said is what I used to do. I don't like that either. Make 2 rectangles, and then each of those 2 rectangles you can just like fold in half. But then I have like a double thick square, little square in the middle. Or you could offset them, I suppose, but then it's not good coverage.
You cut it into 4 triangles and then put 2.
Yeah, this is what I'm talking about. You cut it like this, and then these 2 guys you arrange like this, right? Those 2 triangles, you do that, huh? You see what I'm talking about here? And the other 2 triangles, you do that, and now you have 2 squares of equal size that are half size of the original square, huh? I don't know why I never thought of this before, although like it's not an obvious idea, but I was very satisfied when I thought to arrange my cheese in this way. I didn't tell anybody. I didn't think anybody else would care. But now I told you all. Yes?
How long did that take to figure out? How many years?
Many years, I guess. It's the kind of thing that like I never tried to figure it out before. It just like never occurred to me to do it in this way. Yeah. It made me think something about these like stupid like Instagram life hack videos where it's like that's not terribly useful. Like I think what's satisfying, this is my theory about why the life hack videos are interesting to see. It's not because you say, oh yeah, I'm going to do that and that's going to make my life a million times better. But there is some kind of mathematical satisfaction in finding a cute solution to an obscure problem. And I think this fits that category nicely, for me at least. This is sort of a stupid life hack, but why I like it, I think, is the same reason why I like math in general. There's something sort of satisfying about it. I don't know. Any other thoughts about this? You want to see another one? I actually have another satisfying cutting thing. I hadn't intended to talk about this, but I have I usually bring a sandwich to lunch with me, and my sandwich, I have one of those like plastic sandwich boxes, which is a square, all right? But the bread that I use is like a little too big for the box. The bread is more like this. Like by area, actually the bread is not too big. So I feel like it ought to fit just by area, but it doesn't fit because it's too long and too short. And so for many years, I would cut it like this. I'd cut a little guy off the end and then, put this piece up there, right? Which is a little unsatisfying, that. You ready for the more elegant solution, if you will? Check it out. Start with the bread. Anyone have a better idea? I shouldn't just tell you without, yeah?
Cut it in half and then place it like almost like kind of what you did, but
In half, straight down the middle?
yeah.
Like this?
Wait, never mind, that wouldn't work.
Yeah, they're not gonna fit, yeah. You got an idea?
Kind of like right angles and move the one right angle above the other. So kind of like this, and then move one up and then they hit. Because it moves the one side higher and makes it.
Yeah, I think he's saying what I'm saying. I'm gonna make a diagonal cut, but not through the corners. So slightly offset diagonal cut like that. Is this what you're suggesting?
Yeah.
Yeah. This, I was very satisfied when I figured this out. And then what? Push them sort of together, slide it along the diagonal cut, and the result is that. And then the other one slides up a bit. It looks sort of like that. And now the thing is slightly narrower, but slightly taller, and it fits in this space. Yeah. Satisfying life hacks. Maybe I should be a life hack Instagrammer. I think they're all stupid, but there's something satisfying about it. All right. Any more life hacks to share? Okay, let's get back to the business then. I teach this class in 2 sections, right? As I've mentioned. It means that I have to make sure to take the same amount of time in the second section as I do in the first section, and now I'm worried about, am I going to have to tell them all of this stuff? Or else I will go too far in the second section. We'll see. Okay, let's talk about some variations on the basic idea of the volume of revolution thing. So variations. There's one variation that's kind of simple, and then we have a slightly more complicated variation. One is you can do it sideways sometimes. So for example, and this we're very familiar with from the area between curves things. That is, when I say do it sideways, I mean think of everything as x in terms of y, and then do the same formula, but in terms of, the integral will be a dy rather than a dx. So something like, how about the shape that you get if you start with a parabola, but then you rotate it this way around the y-axis instead of around the x-axis. This is a 3-dimensional sort of a bowl shape. There's actually a name for this. This is called a paraboloid. It's a parabola, but kind of a 3-dimensional thing, all right? And let's say, just specifically, let's say this is the parabola where I'm going, y equals x squared, and I'm going to go from 0 and up to y equals 1. So that much of the bowl shape, all right? How do we find this? So First of all, you realize it's rotated around the y-axis rather than the x-axis. And this is your clue that you have to do this thing sideways. So this is when rotated around the y-axis rather than the x-axis, you have to write everything in terms of y. And then you set up the integral with a dy, right? If you're rotating around the y-axis instead of the x-axis, you use the same formula, but you set it up as a dy. So how do we do that? Write everything in terms of y, including the function. Already my function is written as y equals x squared. I have to solve this for x in terms of y. It would be just the square root. So this function right here, I turn into f of y equals square root of y, right? X equals square root of y. As usual, you should think, at least for a moment, do I need the plus minus because I took the square root? The answer is ordinarily yes, you would, but it doesn't really matter here. The plus or minus would give you either the right-hand side of the parabola or the left-hand side of the parabola, but it doesn't matter because I'm rotating it anyway. So just the right-hand side is good enough for our purposes. All right, and then from here we can just set up the volume integral. It's going to be integral, well, pi on the outside, integral of root y, the whole thing squared, dy. And what are the integration boundaries? They are the values. They are y values this time from the one side of the shape to the other. So it is y equals 0 at the bottom all the way up to y equals 1 at the top. 0 up to 1. All right. And that's how we do it. So this now let's just real quick do the integral. This is an easy integral. I go root y squared is just y. So this is y dy. And then I can, do the 1/2 y squared is the antiderivative. Plug in 0 and 1. So this is pi times 1/2 times 1 squared minus pi times 1/2 times 0 squared. Pi over 2 is the answer. All right, that's the volume of this paraboloid. Any questions about that one? There's not a lot to it. You just have to, solve everything in terms of y rather than in terms of x. All right. Okay, this is the easier of the two variations that I said we're going to talk about. The fancier variation, and this is where actually this, like on our big list, this is referred to as the method with washers, although we haven't actually used that word yet. Washers is what you have to use if there's sort of a fancier type of region that we're talking about. So let's just talk about an example. Let's find the volume of revolution of the area between y equals 2x and y equals x from x equals 0 to x equal 1. Revolved around the x-axis. All right. Because I said this area between, it makes the shape quite a bit weirder than the other examples that we've talked about so far. But I'm going to try and draw these various things. So y equals 2x and y equals x. I can draw those, no problem. It's like that, right? This is 2x, this is x. And from x equals 0 to x equals 1, that would be, x equals 0 is over there. Here, I'll write x equals 1. And I want the area between those two curves, this region right here, and that triangle shape should be rotated or revolved around the x-axis. That's what I'm talking about. What does the shape look like? It looks like I don't know, some kind of a weird. It looks like this on the bottom, but it's round. So if you're looking at it from the outside, it looks kind of like a cone, but it has sort of some of the inside is like drilled out of it. It's like an outer cone with an inner cone taken away from it somehow. All right? It's like a hat. You could put this on your head, and it would stay there. All right? How do we find the volume of this? Now, what is different about this one, which is actually a fairly significant difference, is the height. So typically, you know, our usual formula that we use, I'll just write it over here to remind ourselves. It's this, f of x, the whole thing squared dx, right? Something's got to give with that formula in blue, because here I don't just have one function f of x. There are two different functions that are defining. Well, in this case, I would refer to, you know, the height of one of these is the radius of a slice here, but we have sort of two, there's like a radius on the outside and a radius on the inside, right? If you think about each slice here, how would you describe what each, if I were to, you know, slice this up this way, what would you say the slices look like?
Like a circle, but like with the middle cut out.
With like a circle with the middle cut out, she says. Yeah, this is what, typically we use this word washer for this shape. So each slice here looks like something like that, right? It's like this, it's like one of these, right? This is, you could call that, and it has a little thickness. If you're slicing it up, the thickness would be like the delta x, right? But anyway, this shape here is usually in this context we call it a washer. There's a fancy, like the fancy mathematical name for this. So I'll say this is like a washer. Washer meaning like the little thing that you put a screw into. Fancier mathematical word for this. Anyone know the fancy mathematical word for this shape? It's a sort of a disc that has it's like a ring shape, right? This is called an annulus. Huh? Yeah, that's what it's called. Anyway, each slice looks like this. It has what we are going to call an outer radius and an inner radius, right? There's the outer radius and the inner radius. And how do you find like the area of an annulus, the area of a washer type shape like this? How I would do it I would find the area of the entire circle and then subtract away the area of the inner circle, right? And then that gives you the area of this ring type shape. So the moral of the story here is to get the area of this, instead of just like pi r squared, I would write it this way: pi and then the outer radius squared minus the inner radius squared, right? This is what I said, the area of the outside of the whole thing, and then you subtract away the area of the inner part. That's the same as pi outer squared minus pi inner squared, but I factored the pi out, all right? So instead of just pi r squared, you do pi times the outer radius squared minus the inner radius squared, all right? And what that means in terms of the volume formula, it means the volume that we're looking for is basically this, but instead of just f of x squared, it's going to be the outer squared minus the inner squared. So the volume in this situation looks like the outer radius squared minus the inner radius squared, like so. All right. This is the volume of revolution formula with the washers. So this is the washer formula. All right. All the ones we've been doing so far had inner equal to 0, right? There was no part taken out of the middle. But the ones that we're going to talk about for the rest of today are ones where there is an outer and an inner. And it will always be, up to you to decide which is the outer and which is the inner. The outer is typically like the bigger one. All right. So in this example here, can we say maybe I'll copy this picture down just so I don't have to scroll so much. Here, the outer and the inner. What do you say? What's the outer radius? These, of course, will be in terms of x, like they're individually they are functions. What's the outer radius in this one? Yeah? 2x, right. My functions, remember, were 2x out there and then x over here. So the outer is 2x, the inner is x. All right? And now we should be able to work this out using the formula that you see up there. So it's going to be v is integral. Okay, the boundaries here are 0 and 1, just because I said so at the beginning. 0 on the left side, and then the x value goes up to 1 on the right side. Sorry, I forgot I put my pi on the outside. And then in here, it's going to be outer squared. So that will be 2x squared minus inner squared is x squared. Make sure you handle these parentheses correctly, but it's not such a big deal in this case. 2x, the whole thing squared, means you got to square the 2 and also square the x. So that's actually going to be 4x squared, and then just minus another x squared. So this is pi integral 0 to 1. 4x squared minus x squared. Subtract that, and I get 3x squared. And I suppose you could factor the 3 out if you like, or just leave it there and do the integral. All right? Let's do the integral. Pi in the front, and then 3x squared, the integral of that is just going to be x cubed. Plugging in 0 and 1, and I just plug in 1. Pi times 1 cubed minus pi times 0 cubed. That's just straight up pi. All right. So this is the washer thing with the inners and the outers. Any questions about that one? All right, I got one for you all to try, very similar, and then I have some more fancier type ones. How about, come on now, same kind of situation, but I want to go, this is y equals x, and this is y equals x squared. I want this region revolved around the x-axis. So it's a kind of similar looking shape, although a little bit different because it's got that curviness to it on the inside. All right, see what you think.
Are we going from 0 to 1?
I'm not telling. No spoilers. You'll have to figure out where you go up to this point, wherever that is.
Okay.
You just ruined it.
My bad.
Doing okay? All right, can we talk about this one? It looked like folks were doing just fine. You got to find the outers and the inners. The outer is, in this case, the distance from there to there, which is x, that's the top function. And then the inner would be the distance from there to there, which is x squared, that's the bottom function. You do need to decide where your integration boundary should be. It should start at x equals 0 and go up to here, wherever that is. This is the intersection, the x value where x squared crosses the line y equals x. That's x equals 1, right? You can work that out by setting these equal to each other and then solving for x if you like, or you could just kind of common sense your way through that. It is x equals 1. I happen to know that's the intersection point because 1 squared is the same as 1. All right. So my inners and outers, here the outer is x, the inner is x squared, right? And my volume then is going to be pi integral 0 to 1. Outer squared, that's x squared, minus inner squared, that's x squared squared, like that. All right. This, pretty much everybody was writing this as I walked around. So, and then this integral is not so hard. It's x squared minus x to the 4. That's because in this case you should be multiplying the exponents there. And then I do my integrals. I get 1/3 x cubed minus 1/5 x to the 5, and plug in 0 and 1. Right? You plug in 1, you get 1/3 minus 1/5. You plug in 0, you just get 0 for everything. So my final answer would be that. Whatever that is. You can simplify the fractions if you want to. I don't care about that. All right. Great. Okay, so this is the business with the inners and the outers. Any thoughts about that one? I'm going to make it very slightly more complicated, or maybe a lot more complicated. I don't know. This is still on the general theme of inners and outers. Sometimes the thing that you're rotating isn't sitting on the x-axis, or I should say in a better way. How about rotating around some other axis? I mean, not around the x-axis, but around some other thing. Here's an example. I don't mean x or y. I mean like something entirely different. How about, okay, I have this function, y equals minus x squared. And I want the region from 1 to 2, just because I said so. So from 1 to 2, it's this kind of strange looking shape like that. And I want to revolve this around this line up here. So revolve around, in this case, this is the line y equals 1. Right? That's what that line is. Okay, what does the shape look like? It looks like, so that's sort of on the bottom. It spins up here like I usually draw sort of like its mirror image. Its mirror image will be up there, right? Like that. It's away from the rotation axis because it is, right? So don't draw the upper piece like sitting on the rotation axis because it's not. It's offset a bit. And then it's this thing, you know, if you can imagine that shape being spun around. It looks kind of like a thing you would hold your Christmas tree in or something, right? It has a hole in the middle and then a sort of a nice skirt, if you will. Right? I have a thing like that my toothbrush sits in next to my sink. It's a bit taller than that. All right, made it myself on a 3D printer. How do we do this? It has an inner and an outer, but they are, I would say, slightly non-obvious what the inner and an outer. So we still do the inner and the outer. It's just you have to maybe think a little slightly differently. Still do the inner and the outer radius. It's just like, for example, in this one, the outer is not just negative x squared. I feel like, I usually like to draw a little sort of from the center up to there, that's the inner, right? And then from the center all the way out to there, that's the outer. Or maybe it'd be better if I drew them going down just because, it doesn't really matter, they're the same, but from here all the way down to there, that's the outer, right? These are the inners and the outers. And we should write formulas for them. And these you have to think a little bit differently about. Anybody want to say, what do you think is the let's do the outer first, I guess. I don't know which is easier. It should be, let me just say, the distance of this longer blue line, right? From down here to up here. What do you say? X squared plus 1. How'd you get that?
The distance from the curve to the x-axis, and then added the distance from the axis of rotation.
Okay, yeah, she sort of broke it down as this little distance here plus this little distance here. There are a lot of ways to think about this. I find these, I don't know about you, I find these kind of confusing. The way that I like to think about them is always this, I'm talking about this vertical blue line here. What's the length of that line? I would take the coordinate of the point at the top, the y value at the top, and subtract the y value at the bottom. So I'm going to, in this, you can think of this however you like to think about it, but this is how I'm going to try to reason out. The outer radius, I'm going to always think of as like the top y value minus the bottom y value. This is not exactly how she was thinking of it in a different way, which is totally fine. What's the top y value of this longer blue segment? It's 1, right? So this is 1 minus, what's the bottom y value? It is the equation of the curve. It is negative x squared. Because the bottom y value is determined by the curve, all right? And what's that? This is what she said at the beginning, 1 plus x squared, all right? If you prefer to think it through another way, that's totally fine with me. But this is how I'm always going to think through this outer radius versus the inner radius. All right? And what about the inner? Maybe the inner is a little easier. I don't know. You want this distance right here. What do you say? 1. Yeah, actually, that distance doesn't even depend on x at all. Because no matter where you are, sort of, if you move kind of left to right throughout this shape, that inner distance always is just straight up equal to 1. If you prefer, you can think of it in terms of the top y value minus the bottom y value. This top y value is 1, and this bottom y value is y equals 0. So 1 minus 0 is 1. The inner is, can I write it as 1 minus 0? 1. All right? This can be a little tricky, and I actually have several examples that I want for you all to try to just make sure that you know how to find the outer and the inner. This can be, I find this a little confusing. But anyway, can we just finish off this problem before we do a bunch more examples? So that means the volume is pi on the outside. The integration boundaries, just because I told you they are 1 up to 2, right? The x value goes from 1 to 2. And then on the inside, I want to see outer squared minus inner squared. So that is 1 plus x squared minus inner squared is just 1 squared, I guess. That 1 squared is just a 1. What should we do to do the integral here? What you got to do? Yeah?
You have to do FOIL.
Do the FOIL, yeah. You got to square out that thing at the beginning because when you're just integrating, you cannot just integrate like on the inside of this square. So do the FOIL at the first part there. It's going to be 1 squared plus the middle term will be an x squared and another x squared, which adds up to 2x squared. And then the term on the end will be an x to the 4. And then minus 1 over there. All right. We can cancel the 1s. I got a 1 and a minus 1. And they're all added, so those guys can just cancel. And then I think just do the integral. So it's pi here. 2x squared becomes 2/3 x cubed minus plus 1/5 x to the 5, like that. And I plug in 1 and 2. Right? Feeling good? All right. So plug in the 2, plug in the 1. You get whatever you get. Pi, it's going to say 2/3 times 2 cubed plus 1/5 times 2 to the 5 minus pi 2/3 times 1 cubed plus 1/5 times 1 to the 5. That's that. This is my answer. All right. All right. What I would like to do is I have 6 different examples. Can you believe it? And I want you to just let's just say what the inner and the outer is each time. So the rest of it, like doing the integral, will take you a few minutes. But the hard part in these problems, in my opinion, is just setting up what's the inner versus the outer. How about we'll do this first one together, and then I have many more that I will write down. So let's say this is 1. This region rotated around here, like that. All right. This actually will make a very similar shape to the one we were just talking about. Another one of these sort of Christmas tree stand kind of shapes. All right. But all I want to focus on, just because this is the hard part, what's the inner and the outer? So I would draw it that way and that way, right? What? Not that way and that way. Those are both outers, what I drew those blue lines. Sorry. The inner should go from here, right? That's the inner. The inner radius is sort of like across the gap where there is no volume in that region. The outer radius goes all the way to the outside. What do you think? Someone want to tell us? What's the outer going to be? What do you say?
The parabola +1.
Oh yeah, I didn't tell you. This is x squared. He said x squared plus 1. Yeah, great. I agree. If I were doing this in terms of like the top minus the bottom, I would have written it as x squared minus -1, right? This blue segment here representing the outer radius, the top of it is at x squared. Uh-oh. They want me to restart my computer. Not today, Satan. They tell me this like, I think they want me to reboot it once a month or something, once a week. I refuse. Okay, anyway. Yeah, the top here is x squared, and then the bottom here, the y value is -1. So I go x squared minus -1, which is the same as x squared plus 1. Or if you prefer, I think maybe the way he was thinking of it was this much of it is x squared, and I go plus 1 because that's this much of it. You can think of it either way you like. And what about the inner?
Just negative.
Is it -1 or +1? It should be +1. It's a distance, right? If I was thinking this in the way that I usually would, I would say the top value is 0, and then I subtract the bottom value, which is -1. So 0 minus -1. In other words, 1. I'll write it this way. 0 minus -1, which is 1, right? Yeah, these better not be negative because they represent distances. Although, actually, in this example, if you used the -1, you end up squaring it in the integral anyway, so that wouldn't matter. But the inner radius is 1. All right? Great. This is all I want you to do for these examples. Okay, I'm going to write down 5 more and see how you feel. This again is x squared. This is a strange looking one, but that shape down there and rotated up around this line. Okay. Try and keep them all on the screen at once. everybody can tell what these pictures are supposed to represent.
So scroll up a little bit.
There's nothing there. Oh, do you need to know? That one's also X squared. Maybe you needed to know that. All right, I'm gonna walk around and see how you're doing. I hope you can read everything. Let me know if you have questions. Talk to your friends if you like. Just find the inners and the outers. You don't have to do the whole integral.
Two.
What?
Two.
I'm doing 2 now. What'd you get for 2?
So first we have this X squared plus 4. It's 3 on 4. It's an X squared plus 3 X squared.
This is sort of upside down. How's it going? Okay. Yes. Yeah. So it's no. It's a little. It's one thing, right? It's a little bit unique. Still good here? Yeah, yeah. Yeah, so the distance like from here all the way
We
to
like to see just
It's 3.
Oh, it is. Yeah.
Now, because it's going to change, so X squared must be distance of the X squared. So the distance from the dotted line to the curve, here's the dotted line, and subtract this line from here. That makes sense.
Different way than I heard it. I'm in for them to do it. Okay.
It would just be like
So we get ring.
well, no, it's still
So what's your
it's on.
This, yeah, okay here?
Yeah, this one's good.
This is almost, so the internet is to this. Top, value minus the bottom value. Here, it's gonna be the top. This feeling good here? I have a suggestion about this one. So the outer top y value minus the bottom, top y value minus 3. Oh yeah, it's negative.
Yeah, just thinking about this.
Sorry, this one somebody reprimanded me. This graph is negative x cubed, not x cubed. Although that doesn't really affect the answer, but sorry about that. How's it going? Just turn the page. Doing okay?
Yeah, I think so. I'm kind of confused with this one.
Okay.
It feels like it's almost like kind of opposite. Like, is that the in or is that the outer?
Yes. Mhm.
So would the in be the function and the outer would be the function plus?
I think the inner is real x. The outer. Sorry, where's it? Yeah. The outer would be this needs to be
Just
other
x plus.
Yeah, I would say don't
It's,
try
oh, it's
to-
just fully one.
It's just one, yeah. I would think of it as the y value on top. You're trying to like piece together two little pieces, which
Yeah, it's kinda
it's
confusing.
not
It's
wrong,
just
but
one.
it's
Yeah, yeah.
more complicated. What's going here? I'm gonna give you a couple more minutes and then we'll try and go over these.
First, whatever the distance is.
All right, we got 10 minutes, right? Let's talk about these. So I'm gonna try and maybe I'll put these guys down here. All right, so this one, I am always going to think of this as like the top of the thing minus the bottom of the thing when I'm judging where the top y value minus the bottom one. So in this case, my outer goes from here all the way down to the bottom, whereas the inner goes from here to there, right? That's the inner and the outer in this picture. It helps if you have like a really big picture to be able to draw those things. But anyway, the outer would be, that's this line on the right. The top value here is 3 minus the bottom value, which is 0. So the outer for this one is just straight up 3. 3 minus 0, which is 3. Right? That's the outer radius. And then the inner would be, again, the top value there, which is 3, minus the bottom value, this one right here, which is determined by the curve, that's x squared. So this one should say 3 minus x squared. I hope that's what you got. Any thoughts about that one? All right. This is the hard part of a question like this. If I was asking you, on a quiz or something, I would say find the volume, and then you put that stuff inside of the integral. But that's That'll take you a few minutes, but it's a bit more routine. Okay, this one here, my axis I think everybody knows, I intended for the rotation axis to be right on the x-axis. Anyway, this time the outer is actually 1, right? That longer line there, the top of it is at 1, and the bottom of it is at 0. So this is 1 minus 0, which is 1. The inner, that would be root x minus 0, which is just root x, right? This is the top of there, which is root x, minus the bottom there, which is 0. I think people feel good about that. Okay, great. This one here. So here I have the inner segment looks like this, the outer like that, right? What do you say? Can I poll the audience? What do you say for the outer here? This is x squared, by the way. Yeah? X squared plus 2. Yeah, I would have, as I was thinking this through, I would have said x squared minus negative 2, because negative 2 is the point on the bottom, which is x squared plus 2. And then what did you say for the inner? Just 2, yeah. That's this distance right here. If you like, this distance is 1. Sorry, I don't think this should be 2. Or am I reading the picture wrong? Oh no, it's fine. I'm confused by this extra blue line. That's my page break in the file. Sorry. Yeah, this distance right here is 2. You could do this as the top minus the bottom. That would be 0 minus negative 2, which is 2. All right. Confused by my own lines. Okay, this one here. So if I were to draw them, the outer is that, and the inner is this. What'd you say? What's the outer here? Somebody work this out? What do you think?
X squared plus 1.
X squared plus 1, yeah. Or you could say x squared minus negative 1, which is x squared plus 1. Great. And the inner?
Just 1.
2, yeah. I think the inner is 2. Here I have the top value here is 1, and then goes down to negative 1. 1 minus negative 1. This is 2. Yeah, great. Okay.
Can you explain about the outer on that one again?
So I'm thinking of this big segment here, and I do the top, the y value at the top of that segment is x squared, and the y value at the bottom of that segment is negative 1. So it's x squared minus negative 1, which is x squared plus 1. This is how I think of it. As I was walking around, I noticed some people were thinking of it in a slightly different way, which is, as always, fine with me. Okay, and this time, the inner is like that, the outer is like that. Maybe they're more complicated when they're like down there. I don't know. In this case, I would say the outer, again, I do the value on the top, which is 2. The value on the bottom is negative x squared. So this I would say 2 minus negative x cubed. I just said squared, but it's cubed. So that's 2 plus x cubed. Right, and then the other one, the shorter one there, I can just tell that's distance 2, or you could say that the top value is 2 minus the bottom value, which is 0. So the inner here is 2, all right? That's that. Any thoughts about that? Questions about that one? Can we just, let's actually finish this one. So rather than just writing the inners and the outers. Maybe I'll give you a moment, see if you can actually work out the entire thing here. I intend for these two values are 1 and 2, the x values there. And well, you can tell this rotation axis is up at y equals 2. I'll give you another moment to see what you think. folks seem to be doing all right. I'm gonna write down. So you got to do the FOIL there, right, on the inside. This is a little bit of a pain, but it's not so bad. Do the FOIL on the 2 plus x cubed. Square that out. You get this. And then I'm going to be able to cancel the 4's, right? I have a 4 at the beginning and a -4 there. But otherwise, nothing else can cancel or combine or anything like that. It is integral 4x cubed plus x to the 6. And then we can do the integral pi. We got 4x cubed becomes just x to the 4, and then plus 1/7 x to the 7. I hope that's what you got. And then we plug the numbers. So pi 2 to the 4 plus 1/7 to the times 2 to the 7 minus pi 1 to the 4 plus 1/7 1 to the 7. There you go. That's what I got. Any thoughts about that one? All right. I think that's all we need to say about volumes with the washers. Next time we'll do the shells thing, which is